and today I have the honor to have a little guest. It's right here. That's it. Come here. Come. Hudson is here. Hudson, say hi. My neighbor's dog decided to come hang out with me. There you go. But anyway, today we're going to be working on the continuation of what I had last time. Is there anyone watching? That's an interesting thing. Also, I'm getting a lot of lag. This is very confusing all the time. How do I see whether someone's watching? Stream somewhere? No. Even the message you just sent disappeared. What the fuck? Oh, okay. Cool. So there are people. Good evening, good afternoon. There's a lot of lag I see, but whatever. I hope that is working well for you. So anyway, what I'm going to be doing today is basically the same thing I did the other day. GitHub tempo, justforfunc. Hudson, don't eat the lights. And what we're gonna do is I'm going to copy 38, the episode 38 into episode 39. I'm gonna call it 2. But this one's gonna be linear regression with gonum. And that's the one we're gonna be working with. Okay, so is this large enough for you to read? Because I feel like last time it was not that good. Also, why is that my face on that side? I want to have my face on this side. Good. Okay, cool. Okay, is this large enough? Hello. Cool. Okay, so what I'm going to do is simply go down here, and since I've been doing this for a couple of times already, I'm just going to move all the linear regression part into a different file. Limber.go, and I'm still gonna call it package main. I might consider moving it to a different package maybe later, but for now this is fine. Okay, so this is we have dependency on plotter, which is fine because it's the x, y, so those are the dots that we're gonna be what's up, Hudson? We're gonna be iterating over. So the difference is that we're going to be removing most of this and instead using directly gonum. So let's see what gonum is. I'm gonna try to make it as big as possible. I think it's gonum.org. There you go. So they have GitHub and have gonum/gonum. That's the one we're gonna be using. And the documentation is here. Okay, so that's internal, so we cannot use it. Linear algebra. It's probably not anything linear regression. There's probably nothing that is specifically linear regression, which is fine. So what we're gonna do is we're actually going to convert this operation into operations that are over matrices, because gonum does have a matrix, right? Matrix package, yeah, mat. And the cool thing is that then this allows us to do multiplications and stuff like that, right? So basically what we can do is do the computation of the cost, but at in a different way. So let's start with the cost, actually. So basically this one here. If I do go run main.go, the cost is 896 and 98. Okay, so these the values we're getting. I'm actually going to store that into out.0, because that way I'll check that by changing to a different implementation, we still get the same values in the output. Otherwise, it's probably wrong. Okay, so what we're gonna do is we're gonna multiply m times x plus c. So let's keep it like this for now. Let's pass the plotter. So what we need to do first is convert x, y's into two different matrices, the matrix y and the matrix x, which is actually not really matrices, they're vectors, but that should be the same, I think. Let's see if there's a vector primitives. Yeah, all of this, you see this internal thing here? It means that we cannot even import it. So if I try to import this thing, it would just complain. So yeah, so let's use this one, gonum.org/math. So we're gonna import that thing. Hopefully it will work. Let's make sure that we have the latest version. Go get -u to update to the newest version. And okay, so now we can do math.new dense. This is a dense matrix, basically. Oh, vec dense. Interesting. So you can pass how many positions and the data, or you can do new dense, which is rows and columns and the data. So since we're gonna create a vector, we can do x is the value of this, and so there's gonna be length of xys. And I'm gonna say, yeah, so I can say nil. And if data is nil, a new slice is located for the backing slice. Perfect. So then I'm gonna define y to be exactly the same to Hudson. What are you eating? Come here. Sit down there. Okay, so x and y. So, and then we're gonna iterate over all of the values to initialize those matrices. So we're gonna do x at set vector, no, set scalar, no, set the position I, yeah, okay, so set in a vector, we're gonna set I to be x, y dot x, and y set vec I x, y dot y. Cool. So with this, we have not done much, to be honest. The only thing is we've adapted the plotter x, y's, which is a slice with both values, into two different values, x on one side, y on the other. Okay, so now that we have this, we should be able to do, computers normally, oh, that's a different, have you used Gorgonia? No. Have you thought about it? Yes, and it's actually the next one. TensorFlow does not support variables, so it's impossible to train things with it. I actually found something that was quite interesting. Let me find it for you. It was TensorFlow variables Golang. It was on GitHub by one of the engineers. I'm pretty sure his name, let me find it here. His name was Asim Shankar, I think. Let's see. Asim Shankar. Yes, that's his name. And the conversation was actually on this other account. There you go. So there was on github.com/ Sim Shankar go TensorFlow. There you go. So there's this effort on creating a variable thing that will be added to TensorFlow, but this was updated last time 1 year ago, and the documentation is not good enough for me to use it, so that's why I'm not gonna be using TensorFlow. I decided to drop it, at least for now. I actually sent an email to Asim telling him that I'm trying to do this and see whether maybe there's some way to adapt it or something. But that's why I'm dropping TensorFlow for now, and I'm trying gonum now. And next, probably I'll try Gorgonia, because I've heard it's really good. Okay, so what I'm going to do is, so now we have x and y. We want to do y minus m times x plus c. So y is already y, but m times x. So m is a scalar. So can we do mul vector vector matrix vector scale? Scale vec, that's probably the one we want to do because we're multiplying alpha. The documentation scales vector at placing the result in the receiver. Yes, so that's gonna be x, so scale vec mx. That seems correct. So now we have m times x in here. So m times x. Add scale vec, add vec. No. Maybe translate. Transpose, set vec, sub vec, solve vec. So add, we have two options and none of them is the one we want to do. I want to add a scalar. How do we do that? Sub? No. Add vec dense. So let's see, vec. No, that's actually part of this, right? Type vec dense, add vectors, capacity, copy. Let's see, raw vector, row, view of, scale vec, set vec, slice vec, solve vec, sub vec. In how many places we use float 64? Alright, so that is not the one. Scale vec and set vec. So scale and set, and we don't really have a way to do add, which I guess it's fine, but then I guess that then what we need to do is we need to add two vectors, and then it's going to be x and mv, which v is going to be a vector. So, no, mc, sorry. So mc is going to be c expanded to be a vector of the right size, which is kind of lame that we need to write that, but whatever. So mad new dense. New vec dense, same length, and we're gonna set mc.set vec I to m to c. Okay, so now this is Hudson m times x plus c. So that is the part. Then we can do y times sub vector y minus x. So that is y minus m times x plus c. And this doesn't return anything, it just adds it to there. So now in y we have these results. So next, let's see, next we need to make this square. And in order to make it square, what we can do is actually multiply by itself. So if we multiply element vectors and we do y times y, we're gonna multiply one every single element. So that's gonna be the value of this square, and then we need to sum. Is that a thing that you can do? Mat.sum of y. Cool. That's, wait, that's, can we do no, mat. Nope, mat doesn't do that many things. So sum will return a float 64, and we want to divide that by so that is the sum, divide by that the length of xys. Okay, so this is the new code. So let's see if whether it behaves in the same way. So t out.1. Well, it compiles, which is something, and it does give exactly the same output, right? So we know that this is correct, which is something. What am I doing? I'm re-implementing linear regression, but instead of doing it with pure Go, I'm using gonum. And instead of just doing it with for loops, what I'm trying to do is I'm trying to use matrices. Now the question is, why are you even doing this? Which, great question. And the answer is because normally they should be faster. So let's see whether we can actually appreciate that. Let's create a main test.go package main func bench compute cost. So I'm gonna write a benchmark real quick. I'm gonna try to compare both efficiencies. So for I smaller than b.n, I plus plus, compute cost, we're gonna need to read something. So I'm just gonna get the same value as before. So xys. So xys is this we don't need. So xys, that's gonna be done at the beginning of the benchmark. So this is gonna be, how should I do this? b.stop b.stop timer and b.start timer, because I do not want to time the time it takes to read the data. That's not important to me, that's not relevant, but I want to do xys and let's say 0 0. Okay, so now if I do go test dash bench dot, nope, linear regression declare in this block, because I had not saved. Oh, okay, so I had not saved at all, so that was actually executing the previous one, which is dumb. So let's do go build into linreg. Let's call it linreg and run it again. Do we get the same output still? Looks like it, but out.1. Okay, so out.0, out.1. Okay, so we're still getting the same output. Go test dash bench dot, that will tell us that great, that there's no benchmarks. Why is there no benchmark? Benchmark. Is it because of that? Did I misspell something? Yeah, okay, so now it's actually running it. So that is the time it's taking now. Let's copy, let's see the one we had before. Linreg vanilla main.go. I'm going to copy the previous function we had. I'm gonna put it in the same place. So compute cost, that's gonna be compute cost loop. And let's do the same thing for both. So compute cost loop, benchmark compute cost loop, and see whether one is faster than the other. Which, you know, that's the whole point of making this into use. Wait, this is way slower. It is way slower, right? Yeah. Alright. So that sucks. Oh, but is it way slower because we are spending a lot of time converting these variables? Because those variables will technically be given early on. That might be why. Actually, let's check real quick. CPU profile equals cpu.pb.gz, and I want to run only cost4. Nope. So I don't want to run the one with loop, compute cost matrix. So let's do cost matrix. I don't think I have Google pprof. I don't think I had that installed, which is what I want to use now. Cool. So pprof HTTP 6060 and what is this? cpu.pb.gz. Cool, no execute. Mainly install graphviz. Really? Okay, so let's install graphviz. Brew install graphviz. Is that a thing? Brew install graphviz. Oh, brew formulas is completely down. Nice. Okay, looks like that should work. So let's try to install it. Brew install graphviz. This allows you to visualize graphs, so that's pretty much the whole deal with it. Okay. Wow, this is slow. Damn, things are slow. This is what I wanted to see. So now you can see there's 14 people. Hello, people. Cool. Okay, so this is now installed. So if I run this again, okay, cool. So now we can see where we're spending the time, which is what I wanted to see initially. And actually, can we see the flame graph? I like flame graphs better. So compute cost is spending new vec dense. It's actually spending 46% of the time doing those things. That's surprising, I'd say. The operations themselves, they're pretty fast, but like this part, setback and vec dense, there's the initializations part. Initialization point. So probably this is not a fair comparison, and instead what we should do is get this from the outside. So go into let's see, compute cost XYS. So those are gonna be receiving this as we're doing now. But then, or actually to vex. So, and we're gonna give these two, and we're gonna return X and Y, which are mat.matrix. Okay, so we're gonna just do this part inside of there. Okay, and return x and y. And MC will need to do it inside, because I think that is fair to assume that it will not be part of. No new variables, x and y. Oh, because we already named them. Sure. That's x and y, x time matrix. Because we know these are. Okay, so this is a good practice. If you know the concrete type that you're returning, just use the concrete type rather than an interface. It's just better, because then I can still use those as an interface matrix at any point. But since I know it is a vector, which is also an interface, what does this return? A pointer to vecdense. So those are the things I'm going to be returning. That way this works. And then what I can do here is, so in the linear regression, I'm going to do 2vex of xys, xy, then pass here x and y, and same here, 2vex. I'll probably change that later, but for now I just want to make it so I can have a benchmark that makes a little bit more sense. So x and y, which are mat dot. So here we can say they are vectors, for instance, or even matrix. Okay, so we can do MC needs to be, let's say these are vectors. So then we can do that this is x dot dimensions length. There you go. Then we're going to be iterating here, but actually we're gonna do x, y. I feel like there might be a better way of doing this, but let's say for now like this. So for I equals 0, I x dot len, I plus plus, set C, and scaleback doesn't have those. Okay, so let's go to vecdense, a pointer to vecdense as we had before. And this is x.len now. Okay, so let's run it again. Go build to linreg t out.2. That's it. Out.1, out.2. The cost still the same, which is good. What about our test? Can we do now? So what I'm gonna do is to vex x y s x y, and then do x y. So now we're computing. It doesn't include the allocation of x and y because those are done at the beginning anyway. So I feel like this is a fair comparison. Go bench, go test bench. No, just do a go test bench of both. Before this was 2000, it's still incredibly slow. This is like, the loop is like 15 times faster, which kind of makes me think that if computing the cost is so expensive, maybe it's not worth trying to use gonum at all. Okay, so let's run it again and see where we're spending the time. So pprov, open that again, and flame graph, much better. Okay, so compute cost now spends most of the time doing so the sum and the multiplication of the elements and the subvec. So this is really fast, which is good. The sum is not super fast, but at the same time, I mean, What do you want me to do? I need to sum all the things. This setback and new dense, this part here, all of this is actually because we're not able to add that MC directly. So I feel like maybe, is there any other way? Ooh, cloneback. What is this cloneback? Oh, just to clone any vector, I guess. How do I get the... The definition is gone. That's it. Cloneback makes a copy into the receiver around the previous value of the receiver. Okay, no. Reset, teach, transpose, the capacity, the length, the capacity is the dimensions. Slice vec. Slice vec returns a new vec dense that shares backing data with the receiver that return the matrix starts at I for the receiver. Okay, so that's not what I want to do. New vec dense. This is kind of sad. Clone vec, raw vector, copy vec, scale vec. So scale vec is the one we did. Add scale vec adds the vectors A and alpha times B, placing the result in the receiver. So this is basically allowing us to do M. So you could do, okay, so you could put this together and do M times X, so add scale vec. Add scale vec can do alpha times B plus, so MC alpha is gonna be M. Why did I call it MC? They call it MC? I should have called it VC for vector C, but whatever. So I want to do the C plus alpha, which is M times X. So that will make it directly into this. And this might be faster. Who knows? Super fast because it doesn't compile because I left one line there. Okay, so let's try now. It's slower than before. Yay! That's sad. Time to learn something. Yay! Yeah, so I'm trying to figure out how to make this faster because I somehow expected gonum to be fast. Crazy thing, right? And it is really not. Element-wise multiplication placing the result on the receiver. So that is what we're doing here. Multiple subvec yx. This seems good. Like this doesn't cause any issues to me. It is this part that annoys me. Okay, so let's not count this here and say no, but let's see. Gonum repeat element vector. Doesn't seem like there's an easy way to add one gonum add scalar to vector, because that's exactly what I want to do. Let's see. Rebecca Cohen wrote something about this. So vecdance and advec, setvec, vector arithmetics. So those are, so that is the sum, yeah. Okay, so new vec, advec, adscalevec, subvec. We've used that already. Scaleback, dot product. Actually, a dot product is exactly what we want to do in this case. If we do the dot product of itself, dot product of vectors, isn't this the formula? What is the formula? Is this times speed? So yeah, this should, maybe this makes it a little bit faster. Let's see. So if we do y dot mat dot dot, the dot product of y and y transpose divided by this. Okay, so this should be type matrix as type mat vector. Oh, it needs to be vector, but transpose doesn't return. Really, I cannot multiply two vectors because the transpose of the vector is not a vector. I'm offended. Add const. There's an add const thing. That's exactly what I was looking for, people. Thank you. Add const. Yeah, I mean, but this feels like package float provides a set of helper routines for dealing with slices of float 64. Functions avoid allocations to allow for use within that loops without garbage collection overhead. The convention uses that when a slice is being modified in place, it has the name destination, DST. So I guess that's better, but is this going to use... Yeah, no, those are just loops, right? So it ends up being exactly the same thing. Well, when you're doing gonum, you're actually using... so when you're doing gonum, you're using the GPU. Gonum GPU. Is that the case? That's ASM back. ASM back. What is ASM back? Is gonum is the matrix ASM back? Because I think that's the case, or is the floats package that you send ASM back? Because it doesn't look like that is ASM back at all when I looked at it real quick. Let me see. So if you look at this code, for instance, really. Oh yeah, look at this. Okay, and F64 is defined here. F64 gonum general SM. Okay, so that might be a good idea. Okay, so for those not following the conversation here, Kunde21 pointing out that there's a package called float64, floats, that might be better for us. And I thought that it would not be a good idea because if you're using matrices, we're using specific assembly instructions that can make this be better. Turns out that it is also the case for floats, apparently. And it's also BLAS, which is, BLAS stands for basic linear algebra something, I think. Basic linear algebra subprograms. Oh, really? That's your code? Fancy. Cool. So thank you. So let's give it a try. So let's forget about the matrices for now and go with floats. Okay, so compute cost, what we need to do is we don't need to do this anymore. I guess we can do float 64 in here. And that's gonna be floats dot. All the operations are already on float 64, so we can do x and y. Make on a float 64 of that size. Okay, and then what we're going to do is, so x of I equals x y of I equals this, and then return. So now these are going to be float 64. So then we can do len of x for this. Actually, no, we don't need this anymore. What we can do is, so floats dot, so at time, we're going to multiply, so floats scale. So we're gonna scale and m times x, and that will keep the result into destination, which is x. So now we have n times x. Then we can do floats, add constant, which is gonna add c to x, and that's gonna keep it under x. So now we have this. And then we're gonna floats dot sub y minus x. It's gonna be this here. And now the destination is the first one here, so y holds the value. Let me copy this. And finally, we need to square it. Square, is that a thing? No. Mult. Alright, so we're gonna multiply y times y and floats sum of y divided by this. Whoops. Okay, and this is y times y. So this actually, let's write correctly. So that squared. And that is length of x. Floats dot. Oh, there's a dot product too. Perfect. Okay, so then the dot product allows me to do this multiplication and the sum at the same time. So that's floats dot. Perfect, that's very nice actually. Y, and divide by this. So basically, when you have two vectors and you do the dot product, what is gonna happen is that we're gonna multiply every element with each other. So if you pass both the same vector, you're gonna square every single one of them and then do the sum of all of them. So that replaces the dot, the multiplication, and the sum. So now there's the size. So now let's compare one with the other. Let's see. Damn. Alright, that's pretty good. It's still slower though. It's still slower than the loop, which I'm not sure exactly why. Probably because we are calling something that is, no, I don't really know why actually. Maybe. Oh, Cbro. Hey Cbro. So Kunde 21. Do you happen to know why this one is slower? Like, if you pay attention to these two, sorry, that's not, these two, compute cost and compute cost loop. This one does a loop, and does every single thing at a time. This one uses like fancy assembly stuff. Shouldn't it be faster? Yeah, and somehow now I got even slower. That's probably my computer, but it's better though. It's more like when you write in Python. Yeah, it's less like Go. This looks more like Go, to be honest. This looks more like Python. Also, the thing I don't like, and I understand why it's done because it allows you to do less allocations, fewer allocations, is the fact that you're reusing the receiver. So that makes it more efficient, but this is already very efficient. So try profiling. Yes, that's what I was doing before. Actually, let me do it again. So let's run that cost matrix, which now it's not matrix. So let's change the name. Cost floats. Yeah. So cost floats and pprof that. Not here. I wanted to use that one. Okay, and since I don't like those, I'm gonna use, what is this compute cost? Float scale at const. This is not incredibly useful, I'd say. Yeah, it takes some time. Wait, nanoseconds? Oh shit, yeah, that's actually nanoseconds. Which is not that much, but still. Bounce checking. How could you avoid bounce checking for this one though? You could not. This one I see that it avoids it, but I don't think you can avoid it easily here. Let's see. Yeah, I don't want to check. I don't want to check like the compilation, the result of the compilation, because this one is going to be. Wait, no. What bound checks? There's no bound checks here because it's calling scaling. Yeah, like this. This should be correct. This should work. All right, but this is pretty fast, and I like it. So all right, so let's use this. So I'm just going to drop this one and basically use the same idea for the gradient now and see whether the program behaves faster. So, okay, I'm going to do linear regression. I'm actually going to go into this version. I think this is better, and just move to vex to the main program. So when we do, oh, not that what I wanted to do. I want to call to vex here, to vex of xys. That's gonna be x and y, and that's gonna be x and y. Linear regression. Cannot assign float 64. Cannot assign float 64. What are you complaining about? Cannot assign float. Oh, okay. Yeah, because x is already defined here. Let's call this m. So this is gonna be m. So basically, let's just use the same name on both sides. Okay, and to vex, we're declaring this block. I'm gonna save here. I should stop complaining. To vex, now we can remove it from here. We can remove it from here. And this is gonna be x and y. And compute gradient now needs to accept. So instead of receiving that one, now it's gonna get the same as in here. Yeah, so now what we're gonna do is basically do this part. So the cost is not gonna change. We need to compute this side, which is y minus m, which is exactly the same thing as in here. So now we have this common thing, and then so we should do the m is okay, yeah, so yeah, but okay, so that makes sense. So what Kunde is saying that the cost here might be larger because we're not able to inline the function since we're using assembly, so the inlining does not work, and therefore it makes it a little bit slower. But once we have larger vectors, it might work. It might make it work because we're calling only once, so we're paying that cost of calling assembly only once, which is fine. So that's a good point. I'll try to do a test where I'll just basically multiply the data by like 100 times and see what happens. Could be interesting to see. Okay, so mx, mxc, so we have this part here, y minus mc. So we're gonna need to do one more. It's gonna be dm, it's gonna be make float 64 of length of x. dc is gonna be same. Okay, so dm is gonna be so the sum of minus x, so this is for every single value we need to multiply this times this. So that seems like a dot product here. So floats dot, if we do minus x, why do you do this to me? Well, I can remove that minus and move it at the front, so I can do x, so I can multiply x by y, x by y. So now we putting this into the destination. Now this returns a float, so that's gonna be this here, and that is, oh yeah, I'm stupid, these are not vectors. Okay, so these will be dm will be this 2 times float 64 the length of x. I feel like this might be correct. No new variables. Oh yeah, because it's already defined. Okay, so and then dc is gonna be similar, but dc is gonna be minus 2 times the sum of, just the sum. So floats dot sum of y divided by the same number, and that should be enough. So we should be able to return the MDC. Let's see if this compiles. Apparently it compiles. Go build -o linreg, and let's run it again. Tell out.3. What? Oh, not tell, t out.3. Ooh, we get a different value altogether. So that's totally wrong. There's something wrong. So out.2 we started 3354, and here we just go into a wrong value. Oh, but we're also getting (1.31). So we're actually starting with a different value for some reason. Oh, because that is the result of computing the first gradient. So this is wrong. Okay. Let's see. So y minus m times x plus c is this. It's stored in y. Yes. And then we're doing floats dot x and y. So this times this. And then the sum of all of these things. That looks good. And divided by 2n. So 2 times n. It's more here. I'm gonna call these factor. So this is gonna be times 2f times. So let's see, dm minus xy xd. This looks good to me. Oh, this is not good to me. This is actually minus is this. So one is a dot, because it's dot of x and y. The other one is simply the sum. This should be okay. I don't get why this is not correct. Go build again. T dot 3. Not a number. I don't know what I changed, but I made it worse. Cool. Wow. Okay, so this is very wrong, clearly. Oh, this is divided by. That's an explanation for it. Go build and run again. Okay, I like that a little bit better. Are we getting the same results? 62? No. Okay, so the computation of DC seems okay. The computation of DM seems wrong. So let's see. DM is, so let's move it to something that then makes more sense. So DM, it's the factor that we have. Why did I remove that? That was a bad move. All right. So that was a division. DM is the factor we have. So I'm basically, so DC is here, and DM is here. And now I can remove this part. I don't care about it anymore. So we have DM float. So we're moving this outside, and we're calling that F. We're moving this outside, and we're calling that F. This is correct. This is not. I'm going to assume that the problem is, let's see, dot computes. Oh, hello. Scared the dog. Okay, so let me rewrite this. What do we do? F times floats dot multiplication of, so x and y, and then that's gonna set it into x, and then floats dot sum of x if I'm not mistaken, this should return exactly the same thing, but I'm not sure. So 3, 4. Yeah, so these two things return exactly the same thing, but this should be 1.31, and somehow we're getting it wrong. That's, if anyone sees anything wrong with this code, let me know. Okay, so no, this seems correct. Am I doing something wrong with the values of... So if X or Y were not the good ones, this would not work at all. Sub is setting here at const Cx mx c. I'm about to give up. Gm float sum. That's the part that I don't like about the fact that reuses the receivers, is that you have side effects everywhere, so that makes it quite hard to reason about the code itself. Not a huge fan of that, but that's how things are. X times let's try this actually. Can I do... I'm gonna try to debug. Like YOLO. Can I find Delph debugger? Oh yeah, Delph is not installed. Can I do brew install Delph and pray for the best? Maybe it works. Actually, I think Delph is written like this. No. Brew install Golang Delph. I know that was a thing that worked. Oh, okay. Go Delph, Delph, Delph. Sure. Go Delph, 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 Delph. Cool. Let's see if that installs it correctly. Oh no, that installing Go 1.10. Whatever. Let's see if that works. Hudson. While this installs, the good thing is that I have a puppy to play with. Oh, look at this boy. Is pulling that negative out correct? Try float scale. So I would say it's correct, because if you multiply this minus 1 and this a multiplication, I mean, it feels correct. Maybe it's not. Let's try. It's an adorable puppy, right? He just learned how to give the paw. Silence. I know. Okay, so let me try that. So what he was saying was basically, what if we try float scale of x first? So float dot scale minus 1 of x. So that will multiply x by minus 1. So basically we're moving back to that thing here. And so that will be this, and then yeah, so that is what you're saying, I think, right? Okay, go build, and that doesn't look very good. I think that we have the same problem again. Okay, so yeah, no, this is not correct, because this is returning 0 for for that for the gradient, which is not correct. The gradient should be minus 1.31. That's why we're moving in that direction. Let's see. So yeah, no, this we can move back to what we had. Is this what we had before? Go build and run. Yeah, that's the same. Yeah, that's exactly the same. And let's see if I can do the debugging now. Maybe it works, maybe it helps, maybe it doesn't. Cannot find Delve debugger. It is installed though. I'm just gonna kill it and open it again. Code. Puppy dog debugging. He's not very useful. No, you're not very useful, are you? No. He doesn't know how to debug much. What's this? Well, I don't wanna know. Okay, so let's try debugging, and if this doesn't work, I'm gonna need to go walk the dog because he's getting. Nope, doesn't work. Okay, so yeah, so the puppy needs debugging. Technically not debugging, but it's the shitting. So I'm just gonna take him out. Otherwise, he's gonna start crying in a minute. But this is sad. I expected this to work. And so yeah, have a look, and if you see anything that is obviously wrong, like I don't think that this is wrong, but you know what? I'm just gonna send it to. I'm gonna create a new branch. Send it to as a PR so you can have a look, and if you find something that seems wrong, just let me know. So work in progress, Lindra gonum, git add. Sure, let me move the binary. We don't need the binary nor 39 nor the CPU. Yeah, the rest is fine. So git add, git sm, and of Twitch, git push origin. Fuck, I thought I had created that git checkout. Why didn't that change git status? I'm on the branch. This is okay. So that's a bug. Whatever. Git push origin. Cool. And I will create GitHub just for func. Gonna create a PR so that way if you feel like having a look at it, please do. What is compute gradient not returning the right values? Okay, so yeah, if you want to have a look, there you go. And if not, that's fine. I'll keep on playing with it a little bit later. But I need to go take the dog out, otherwise she's gonna get mad. Alright. Gonna get him to say bye. Come here. What are you doing now? Come here. Come. Come here. You do it all the time, and now you don't want to do it. Alright. So this is Hudson. Say bye. There you go. Okay, have a good one. How do I stop the... I'm always confused. Okay, there you go. Bye.